subscribe to our YouTube channel, Joy Learning TV.
You are welcome to SHS2 on Joy Learning. I'm so happy to be with you once again, and this is SHS2 Core Mathematics. And today we want to look at Mensuration 1. You know, in our syllabus we have Mensuration 1 and Mensuration 2. And so we want to start with Mensuration 1, and because it's a very complicated topic, we want to have it part 1, part 2, and then probably part 3. But for today, we want to look at part 1. So Mensuration 1, part 1. My name is Evans Odei. And as usual, we want to always get ready with our notebooks, our pens, our calculators, and then we set the ball rolling. So by the end of today's lesson, you should be able to define a circle as used in mathematics. Not a circle as we use in any other language, by the way. So identify and explain the parts of a circle. Demonstrate the concept of pi. We are going to investigate pi. How did it happen? Where is it coming from? Then also we discover the rule in calculating the circumference of a circle, length of an arc. Then we also discover the rule in calculating the areas of a circle, sectors, segments, and perimeters of sectors. That is our objective for today. So by the end of this, you should be able to have all this at your fingertips. So we'll start as usual with status. We'll do our normal mental exercise, something to energize our brain cells so that we can do mathematics. Now the question I have for you is simple. Can you have this particular squares? And then I want you to put in numbers 1 to 8. Numbers 1 to 8. No 0, no 9. That means no 10. Because if you don't have 0, you don't have 9. And you don't have, that means you cannot get 10 as well. So you put in 1 to 8, each in the squares so that each side adds up to the middle number. It means that when you put in the numbers 1 to 8, no matter you have 9 squares, and one has been taken care of by the 12. And so 12 is not part. When you add the numbers you place on the top should be equal to 12. Whatever is here should add up to 12. All this should add up to 12. This should add up to 12. This should add up to 12. So how will you position the numbers 1 to 8 in such a way that this will be perfect? I mean, you add this horizontal, vertical here, vertical there, horizontal there. This and this must add up to 12. This and this must also add up to 12. And I'll give you some few seconds. You can take a screenshot with your phone on a TV, draw it and see if you can get the answer. I'll give you just 60 seconds. Let's see if you can do this. All right, I'm sure you've been able to struggle to put in the numbers, and let's see what the answer is, or what could have been the answer. If you do it very well, you should get something like this. Not necessarily having 1 here and 8 here. Maybe your 1 will be in a different square, but then it will still add up to give you the 12. So you can see here that 1 plus 8 plus 3 is 12. 3 plus 7 plus 2 is 12. This 8 here plus 4 here will give you 12. 5 plus 7 also will give you 12. Then when you go to the vertical side here too, you get the same as 12. All right. So let's get back to work. What is mensuration? Mensuration, what is it? What are you supposed to learn about it? So let's understand the concept or the topic itself, the meaning of the topic. When we talk of mensuration, it's a whole branch of mathematics. So not just a topic to be treated in secondary school, it's a whole branch of mathematics that deals with measurements of perimeters, of areas, of volumes, of various geometrical figures. So a base of application of plane geometry is going to work in mensuration. And so mensuration 1 basically deals with all plane figures and their areas and then the perimeters. Then mensuration 2 will deal with areas and volumes of solid figures. And so for mensuration 1, we are going to look at only plane figures. Then mensuration 2 will look at solid figures. And so today we are looking at mensuration 1. And mensuration 1 always starts with the concept of circle. Let's understand circle as used in mathematics. So what is a circle? And I'm sure you might have defined it severally using different definitions. But then as far as maths is concerned, and as far as this particular course, that is mensuration as a topic is concerned, we want to define circle as this. It is a locus of a point equidistant from a fixed point. Again, circle is a locus. And now the word locus here simply means that a path that we trace, okay, or a path a point traces as it obeys certain conditions. And the condition I'm giving this one is it must move from a fixed point equidistant. Okay, it must be equidistant from a fixed point. That means the path that is being traced must have equal distance from a fixed point. So you can see from the diagram here that P is moving in such a way that it's keeping equal distance from the point A, and that is circle. So circle is a locus of a point equidistant from a fixed point. Now let's look at parts of a circle. We've seen a circle like this. It's a plane figure. And so what are some of the parts we can see as far as circle is concerned? Number 1, circumference. Circumference is just the path being traced. So circumference simply means total distance around the circle. So any circular object, the total distance around it that forms the circle is called circumference. So by definition, we say a circumference of a circle is the total distance around the circle. Circumference can also be referred to as the perimeter of a circle. That means total distance, perimeter of a circle. In real life situation, for example, if I have this clock here, you can see that it is a circular in shape, or circular in shape, and the total distance around it like this becomes the circumference. This bow here, total distance around it becomes our circumference. The tire of a car also has got circumference, and it tells you the distance that it travels. This bicycle tire also gives you circumference as such. So circumference, we see it everywhere. Every now and then we observe circumference. Another word or part of a circle that we'll be using in the course of learning this topic is arc. So arc simply means part of or a portion of a circumference. So I can take a small portion like this, it's an arc. I can take a very big portion, it's an arc. So far as the portion that I take doesn't complete the circle, then it becomes an arc. So an arc can be very small or big. But the moment the arc goes and comes back to the original position, then it's no longer called arc. We call it circumference of a circle. And so if you look at this object here, we can have a portion of this tie that will be the arc. And sometimes we'll be asked to calculate the length of an arc taken on a circle. And so this object here, I can pick the length of the arc here. And so that is arc for you. Then the next word is called radius. Radius. Radius simply means any distance, or when you draw a line from the center of a circle to the circumference, from the center of a circle to any part of the circumference, the distance over there is what we refer to as radius. So it's the length of a straight line drawn from the center of a circle to a point on its circumference. The plural form of radius is radii. So I can say 2 radii, 3 radii, 4 radii, 1 radius. Great. So in real life situation, if I take this bicycle tie from the center here to the circumference here becomes our radius. So more or less we can say that the spoke of a tie or the bicycle tie gives us the radius of that tie. That is, when we're looking at the internal circle, okay, it gives us the radius of that. And when you're doing robotics, sometimes you need to calculate how the tie can move in a number of distance, in the particular distance. And so all this aspect of math goes into robotics, and we do a lot of calculation as such. Then we have another word called chord. Chord. And again, we'll be using chord a lot in the concept of mensuration. Chord. Chord simply means anytime you draw any line from one point on the circumference to the other point is referred to as chord. So from a point on the circumference to any point on the other side of the circumference is referred to as a chord. So a line that joins 2 points on the circumference of a circle is called chord. Now take note of this. It divides a circle into 2 areas. Anytime you draw chord, you get 2 areas. Okay, and that area, or each of those areas, is referred to as segment. And so when I draw a chord, I create 2 segments. We'll understand segments and we'll learn how to calculate the area of a segment. Now again, a chord that passes through center of a circle is called a diameter. So in future, if I say diameter is a chord, true or false? It's true, because diameter is a special chord that passes through the center of a circle. So if I draw any line from one point to the other point and the line passes through the center of the circle, that chord is called diameter. Beautiful. So that is diameter and chord. So by definition of diameter, we'll say that diameter is just a chord that divides a circle into 2 equal parts. All right, so we can see a chord here with this particular cake. I don't know whether it's bread or cake, and you cut. So the line that has been used, or the line from the point here to that point, represents a chord. And for that matter, the piece over here is the segment, or the area of the segment. So if I'm to eat this part, I'm eating one area of the segment, and the other side becomes another area of a segment. We'll talk about that very soon. So what is diameter? By simple definition, we are saying it is a length of a line segment joining 2 points on the circle and passing through the center. All right, so we can see diameter here from the point of this tie to the point here. As it passes through the center, we can see the diameter of the tie. We can see the diameter of this row sign or warning sign. And so diameter helps us a lot, and engineers do a lot of designs, and they need to apply this concept of mensuration, knowing the diameter, the length of it, and then learning the segment and co. Right, so talk about segment. Like we said it earlier, the moment you see a chord, then it means we have 2 areas, and each area is the segment. So you can see from the diagram here, you can see a portion that is orange, and then the other portion is ash. And so we see 2 segments. And once we have segment, if the chord is not passing through the center for us to get exact halfway through, we always get a minor segment and a major segment. But the moment it passes through the center, they will create the biggest segment, which is the semicircle. All right. So here we can have a chord, our segment minor, and then the segment major. And so by definition, we can say a segment of a circle is an area bounded by an arc and a chord. Very simple. Bounded by an arc, because there's an arc here, okay, and then a chord. So the middle is what we refer to as a segment. So once again, you can see segments here as we introduce chord. Right. Now let's talk about another area of a circle or part of a circle called sector. Now talk of sector, all we are trying to say is when we have two radii, okay, bounded or with two radii with the length of an arc, enclose an area, and then the area is referred to as a sector. And again, we can always have two sectors, one minor and one major. So you can see the bigger area here being the major sector, and then the smaller being the minor sector. So when you have two radii and a chord, the area created by the two radii and a chord gives us the sector. So by definition, we'll say that a sector of a circle is a region, right? A region or an area bounded by two radii of the circle and an arc. Good. So you can also see from here that as we have two radii and then the arc is moving, you see two sectors, one small, the other one big. So we always have the minor sector and the major sector. So you can see different sectors being created here, a sector here and a sector there as well. Okay. And so in more practical lessons, we can have our pizza sometimes cut in a sector form, and we like enjoying pizza in this way. So that is sector for you. So this is a sector. So you can see our arc here, and we can see the radius, the other radius, then we get our sector. All right, then let's talk about a special sector called quadrant. A special sector called quadrant. So let's have a radius here, another radius here. Ideally, we'll call the space here sector. The space here sector. But because this sector has the central angle to be 90 degrees, we give this sector a special name called quadrant. And so quadrant simply means 1/4 of a circle, or 1/4 area of a circle. All right. So I can ask a simple question. How many quadrants can we get in a complete circle? How many quadrants? Perfect. 4. Because if it's 1/4, that means it's divided into 4 equal parts, and each area is called quadrant. So quadrant is a sector having special central angle being right, or 90 degrees. Then we have the last part of a circle we want to talk about, even though not directly a part of a circle, but we want to introduce this because we'll be using it as part of the things we are supposed to learn. That is tangent. Now let's have a circle and locate a point on a circumference. Here I want to call it the point P. Now, if I draw any straight line from anywhere and passes through the point P on the circumference, the straight line that meets the point on the circumference is called tangent. So this is tangent. Again, it is a line drawn, a straight line drawn to meet a point on the circumference of a circle. Is called tangent. So by definition, we can say a tangent is a line that touches a curve or a circle at a point and does not cross the curve or the circle. The moment it crosses, it's no longer a tangent. This is called secant. It's called secant. any line that passes through a curve or a circle is called secant. When the line starts from one end of the circumference to the other end of the circumference, then we refer to that as chord. That is what we've just mentioned, chord. So we have chord, we have secant, and we have tangent. Tangent touches the circumference, secant passes through, chord starts from one end of a circumference to the other end. It doesn't go beyond that. Beautiful. So in summary, this is what we are studying so far. We've talked about circumference, we've talked about segment, chord, an arc, you can see that here in the yellow, the diameter passing through the center, the area of a sector here, quadrant also is there, then the line, the blue line here referred to as radius, and then the mauve line here refers to as chord, and then the area segment, and then the circumference. So this is the summary of what we've done so far. Let's continue. Pi. So why am I starting the whole concept with pi? After understanding what a circle is and we've done the parts of a circle, we want to talk about pi as a subtopic. Yeah, very important as a subtopic. Normally, we don't see it as a subtopic in our course, or maybe we are learning mathematics, but I want to treat it as a subtopic so that when you understand the concept of pi, you will understand why it's being used in the formulas that we generate as far as the area of a circle, circumference of a circle, the rest. What is pi? Big question. What is pi? The symbol for pi is this one. Okay, that is a Greek letter. And if you look at the Greek alphabet, like we have our English alphabet, A, B, C, D, which is the English alphabet. In Greek too, we have some symbols like alpha, beta, gamma, omega, pi, theta. Okay, so pi also is a symbol that comes from the Greek alphabet. So what is it? What is it? Now, before we understand what is it, I want you to consider a circle with a diameter and a circumference. So let's pick any object in our environment, be it a milk tin, Milo tin. Let's try to measure the diameter of the circular part and also measure the circumference. Maybe you can use a string. Here I'm having a GeoGebra and I can pick various diameters with respect to their various circumferences. For example, if I look at 2.5, its circumference is this. Can you see that? And so if we pick different circular objects, measure their diameters and measure their circumferences, and we try to do this, let me just give you an instance of what I did. I picked this, I used the GeoGebra to measure the diameter of a circle and its corresponding circumference of a circle. That is what the figure that you saw. This animation is telling you that we are having, let's say, a diameter of 2.5 with corresponding circumference of 7.854. So I took different diameters with their corresponding circumferences. So if I divide, I try to divide the diameter, so divide the circumference by the diameter, then I recorded the value. So in the house, at your free time, I want you to just pick a milk tin, Milo tin, any circular object, a perfect circular object. Try to use a string to measure the circumference of it and the diameter of it and record the two numbers. Divide the circumference by the diameter. You observe something, and that's what I'm doing here. So when I divide the 3.14 by 1, I'll still get 3.14. Then I divide 4.0562 by the diameter, which is 1.2911. This was the result. And this was calculator answer, because calculator can give you, I think, only 10 digits. If you try to open it up to a bigger number of digits, you can see more numbers. So for the second one, 4.7124 divided by 1.5 also is giving us 3.1416. Mathematicians were observing this pattern of numbers. They pick any object at all which is circular, measure the circumference, the diameter. When they divide the circumference by the diameter, they observed they were getting almost the same number, similar in terms of their number of digits and then the digits that are involved. So observe 3.14, 3.1416, 3.1416, 3.1416, 3.1415, and so on and so forth. So when you do all this division with your calculator, you observe that the numbers seems to be repeating. I mean, it's almost the same. So it's like there's a constant answer we are getting from the division of a circular object, its circumference by the diameter. So they said, okay, it looks as if you are getting a constant value anytime you pick a circumference over diameter. So if that is the case, it's a constant value. So let's give it a name. And so they gave it the name pi. If you draw a graph of the diameter values and that of the circumference, you get a very straight line, I mean a perfect straight line. It tells you that as you increase diameter, you also increase circumference. So by definition of pi, we are saying it's a mathematical constant, which is the ratio. Ratio means division, right? Ratio of a circle's circumference to its diameter. And it is represented by the Greek letter pi. Beautiful. And so pi simply means circumference over diameter. And that is how pi came into existence. It's just a constant value that they were observing. I mean, they were seeing continuously as they divide circumference over diameter. So if you look at the pi, I used my computer to generate, to go beyond the number of digits that a calculator can give. Then I saw these numbers. Observe these numbers here for pi. No repetition, right? No recurring. And this number continues till thy kingdom come. It's infinity. If I ask you to mention pi, and you start mentioning pi like 3.14159265, you keep on mentioning it. I'll go to the house and come back, you'll be mentioning it. 3 days later, I'll come back, you will still be mentioning it. 10 years later, you will still be mentioning it because you will not finish mentioning the number. In fact, if anybody sees you mentioning a number for a number of days and you are still in the room mentioning number, what would they conclude? That you are growing, you are going mad, or you are being insane. And so you are being irrational. And that is why pi becomes an irrational number, because a number that will not terminate and will not recur in terms of its decimal values. And so pi is an irrational number. Mathematicians realize also that anytime you pick a number 22 divided by 7, the results for the first 3-4 digits is similar to that of the pi. Look at 22 over 7 from my computer. I had 3.142857.1, and this number, observe it, repeats. Check. 3.142857, 142857, 142857, 142857. So you see that it's repeating. And so we call it recurring decimal. It's called recurring decimal. So we can approximate pi to be 22 over 7, but we can't say they are equal. So don't write pi is equal to 22 over 7. Don't ever write that, because they are not the same. Pi is an irrational number, whilst 22 divided by 7 is a rational number, because it recurs, and all recurring decimals are rational numbers. All terminating decimals are rational numbers. but non-terminating decimals and non-recurring decimals are called irrational. So we can't equate pi to be 22/7. We can take it to be 22/7, but we can't say they are exactly the same. So it's better you use the symbol approximate to show pi. Wow, that is someone's job. Somebody sat down to generate pi up to 1,000 digits, and this is the outcome. It tells you that pi has no end. I've also come across somebody who have done it for 1 million digits, and you love to say it. It has no end. It's really an irrational number. Just for fun, observe this. We say pi is 3.14. Okay, like approximately to maybe 2 decimal places, we can say 14. And observe the pi that we eat also is here. See, math is so interesting and so fun. If you turn this 3.14 upside down, it reads pi. It reads pi, P-I-E, like we are eating the normal pie. So the pi we know in mathematics, and we try to write each figure, we turn it upside down, we can also call it pi as we eat. All right. Okay, so let's talk about circumference of a circle. What is circumference of a circle? We've already defined it, so we want to look at how we can calculate it. Now, for circumference of a circle, we want to start from here. We know that pi is circumference over diameter, or divided by diameter. If you try to make circumference the subject from this particular relation, you are going to see circumference is equals to pi d. That is, if you do cross multiplication, right? 1 times c, and then pi times d will give us pi d. But we know that 2 radii always create, or 2 radii that passes through the center will give us a diameter. For example, if I have this circle, and I have center here, and I have this as a radius, and another one as a radius, I've created a diameter. So 2 of this radius, okay, or 2 of the radii will give us 1 diameter. So we can say that, okay, d is equal to 2r. Beautiful. It's true, right? Good. If we substitute d by 2r in this relation, we can say that c is equals to 2 pi r. And I'm sure this formula is very known to you. I mean, you know it already, that circumference of a circle is 2 pi r. So this is not magic. I mean, they didn't quote it from somewhere. It came from the definition of pi. And so by the definition of pi, we can now know the relationship. So right now, tell me, if you give me a circular object, and you tell me that this circular object has a radius of, let's say, 7 centimeters, I should be able to tell you the circumference of that circular object by the relation, because I'll just multiply this by pi, which is 22/7, that's approximately 22/7, then times 2, so that I can do this and get 44 centimeters. So if I know radius, I can tell you the circumference. And if I know the circumference too, I can tell you the radius of a circle. Good. Now that we know the circumference of a circle to be 2 pi r, if I have a circle and I want to know the length of an arc, if I take a small portion of the circumference and I want to know the length of it, I want to start with this. You see, look at this object here, right? Now, if I move the circumference, or maybe the point C along the path, okay, and I trace the path, then I'll be tracing some arc, right? So you can see that I'm tracing an arc here. So as this arc is going, you see that the central angle here also increases. So it means that the length of an arc is directly proportional to the central angle. So I increase the central angle, I will increase the length of an arc. So I can never find the length of an arc without considering the central angle, which is seriously part of it. You see that? So that is what we are going to do. So we can say that if that is the case, if I have a circle and I have a radius, another radius, and I have the length of an arc, which is the red line, which we normally call the L, and I have the theta, it means I can make this statement that theta over 360, because this theta here is part of a complete circle, which we all know that every circle, when it's complete, the interior angle is 360. So part of this angle, which is theta, over the total angle 360 times a portion of the circumference, which we say 2 pi r. So by definition of length of an arc, we say theta over 360 times 2 pi r. We can always find the circumference, so the length of an arc, the length of an arc. So keep note of this formula. We'll be using it to solve questions. Then area of a circle, for that we all know, right from primary school, everybody knows area of a circle. Surprisingly, I always ask this when I ask any student, especially at the senior high school, even if the person doesn't like mathematics and hate mathematics so badly, ask the person what is the area of a circle. He will quote the formula for you. It's the most popular formula everybody knows, right? So area of a circle, we know that to be, if I have this circle and I want to look at the total area, the space that the circle is occupying, okay, the space. So the space, and if I know the radius, I can easily say that area of a circle is pi r squared. We can generate this. I have a lesson on YouTube. You can search for it. I've done this particular formula generation, how it came about, and you can watch it and it will be of great help to you. So area of a circle we know to be pi r squared, right? Then we talk about area of a semicircle. Area of a semicircle. If the total area of a circle is pi r squared, then the semicircle is very easy to handle. It means if I have this whole area to be pi r squared and I look at halfway through, all right, then this half area is going to give me divided by 2, as simple as that. So I get the area of a semicircle to be pi r squared over 2, or half pi r squared. Then we want to talk about the area of a sector. We know the length of an arc. We want to look at the area of a sector. Once again, this is a sector. And this sector can be small or can be big. But whatever be the case, the blue portion of the sector increases with the central angle or decreases with the central angle. As the angle goes up, the area becomes bigger and bigger. Okay, so once again, we cannot define the formula for finding the area of a sector without considering the central angle. Okay, it doesn't matter the radius of the circle, but so far as the angle keeps on changing, varying, okay, then our sector also will vary, whether it will become big or small. And so by that definition, we will say that if we have two radii and an arc, and we get the area of a sector with a central angle, we'll say, okay, a portion of the angle is theta. Then the total area of a circle is pi r squared. So if we are looking at the portion of the area to be called the sector, then we have to say theta divided by 360 times pi r squared. And that is how we define area of a sector in terms of calculations. If you want to calculate the area, you should go by this formula, right? Then we want to look at area of a quadrant. Remember, we are doing mensuration 1. And part 1 is what we are looking at. It's a very complicated topic, a very broad topic. And so we are trying to pick them little by little. So part 1, we are looking at the circle, the parts of a circle, how to find the areas, perimeters of the parts. And all this we are calculating. We've already defined where they are in circle. So we are here with quadrant. Now with quadrant, we said it is quarter of the area of a circle. So if the whole area is pi r squared, and I'm dividing pi r squared by 4, then simple, I can just say the quadrant is equal to pi r squared divided by 4, or 1/4 the area of a circle. Good. Then we want to look at the perimeter of a sector. Now we want to look at all these formulas and how they came about. Then we'll see questions and see how we can apply each of them in answering questions as far as mensuration 1 is concerned. And remember, this is still plain figures we are dealing with, right? Plain figures we are dealing with. So we want to look at how to find the perimeter. Of course, the perimeter simply means the total distance around the sector. Okay, whether the sector is a major sector or minor sector, the formula remains the same. Just that the central angle will change if it is a major sector, and it will be the theta if it is a minor sector. So let us assume that I want to find the area of this major sector. I'll still go by saying theta, and the theta is going to be the theta over here, right? So it will be 360 minus this theta here, which will give us the angle here, divided by 360, then times the same pi r squared. Simple. Then I'll get my measure that. But then I want to find the perimeter. The perimeter. So we are saying that for perimeter, if I can add the radius and then add another radius and add the length of the arc, I should get a perimeter of the sector. Very simple. So radius plus radius we know is going to give us 2 radii, right? Plus our L, and the L already is known from the beginning as theta over 360 times 2 pi r. So when you put all this together, we can say 2r plus theta over 360 times 2 pi r. And that defines the total perimeter of a sector. And again, if the perimeter of a sector we are looking at has to do with the major sector, then it's very simple. We just have to change this theta and make it 360 minus theta so that we will know the bigger angle. Then we want to look at an area that is a bit complicated for students to grab. That is the area of a segment. Area of a segment. Now, for area, we want to look at it in terms of the minor segment and then the major segment. Remember, we've already learned that segment is just an area created after we draw a chord. Or anytime we draw a chord, we create 2 different areas called segment. So we have the minor and then the major. So let's have the minor segment. That's the shaded portion. You can see the shaded portion here. That is our minor segment. You want to know what to be the area of this part of the circle. That's what you want to know. What is the area of the part of that circle? So we want to do this. Now, I want to create this particular line, I mean the radius here. When I create this one, observe it. This line that I've created, which is the line AC and then the CB, together with the length of this arc, gives us a sector. Look at that critically. The whole of this is called sector. But you know that. I'm including the segment and then the triangle. So the triangle at the top plus the segment together gives us a sector. And we know sector to be theta 360 times pi r squared. So if I'm able to know the area of the triangle here, which is this area here, and I subtract it from the area of this sector, then there will be a remaining portion, the area of the shaded portion. That is the segment. That is all I want to do right now. That is all I want to do right now. So theta is here. Now, you can see that I've now painted the two together, the triangle and the segment. Now together, all this is the sector. So I will say that area of a segment can be defined as the area of the sector minus the area of the triangle ABC. It's as simple as that. So how do we find the area of the triangle ABC? And that is where we have to apply a different approach. I'm sure you will tell me the area of a triangle is half base times height. But that will not be used because we don't have the height of the triangle. But we are going to use the area of a triangle when we have one of the interior angles given. And that is normally given as half r squared sine theta. Now, if you are dealing with, let's say, trigonometry, you will understand this perfectly because there they will use trig to prove it or vectors to prove it. But for now, because we are doing core, we want to just quote the formula and then we apply it in solving questions. So theta over 360 here represents our area of the whole sector. Then half r squared sine theta gives us the area of a triangle. And I'm sure this one also was given to you during your plane geometry lesson. If you don't have it, go to YouTube. You'll see plane geometry lesson. I did it with revision show. So you can check revision show and go to plane geometry 1 and 2. You will be able to know how this formula came about and you can add it to your facts. Good. So that is the area of a segment when we are dealing with the minor segment. Now let's try this with the major segment. Major segment, that is simple. So this time around, we have our chord and we are referring to the major part, not the minor part. We are looking at the major part. So the major part is going to be like this. So what I've shaded here, let me come again. What I've shaded here is the minor part. That means the remaining green part becomes our major segment. When I draw my two radii, then observe this. You realize that if I look at this portion of the circle, it defines the major sector. Check it. The portion here without this part, the portion here alone defines major sector. Good. If that is true, then we'll see that this small triangle here is adding up to the major sector to give us the whole major segment. That is what I want you to observe. Let me repeat that portion again. What I'm saying is that without this triangle, the green portion of this area is called major segment. The moment I draw this triangle, then the triangle splits that segment into two areas where the area up here becomes a major sector. And then the small area green here also becomes the area of a triangle. So for me to find the major segment, it's as simple as just adding the area of the major sector plus the area of the small triangle. Together will give me the total area of the major segment. I think it's very cool. It makes sense, right? Beautiful. All right, so we have this plus that to give us that. So our area of a segment becomes major sector plus area of a triangle. So we can write this as 360 minus theta because I'm dealing with the major sector. Divided by 360, then pi r squared. Then I will just add the half r squared sine theta. Good. Now, that is all for the formula work as far as this course is concerned. Now, the rest are going to be questions that we can answer using the formulas. As simple as that. So question number 1 is simple. It says a moving disc of radius 14 centimeters. So if this is your disc from the center here to the circumference is 14 centimeters. Find the circumference of the disc. and the area of the disc. It's a matter of quoting the formula. Circumference is 2 pi r, that is c, and knowing that your pi can be equivalent to 22/7, or you can just say 3.14. Normally it's given in the question. If it's not given, it's a constant, so everybody knows the constant. You can just quote it and use it, and you get your answer. When you make substitution to this, you write your circumference will be 88, and your area will be 616. Very simple, right? Again, circumference is equal to 2 times 22 on 7 times the radius of the disc given as 14. So we get a 14 there. They will do a simple calculation, then you get 88. Then the area, which is equal to pi r squared, again 22 on 7 times radius 14, then squared, and you simplify that, you get 616. Now, question number 2 for you to try. So you can take the screenshot. I'll give you the answer. Then you just put in the formulas. You put in the figures, and you get the same answer. Area of a circle is given as this. You want to know the radius and the circumference. I didn't give you the radius. I didn't give you the circumference. So I want you to find the circumference and the radius. And what do? You just have to pick your formula. The area of a circle is pi r squared. And what is the area? 154. What is pi? 22 on 7. What is our r? We don't know. So here you're only making r the subject. You do cross multiplication, you divide both sides by 22, you get your r to be 7. Actually, to be 49, so to be r squared equals 49, they will take your square root of 49, and that will give you 7. Good. Right, so I'm almost ending my lesson for today. I want to give you the questions, take screenshots, I'll give you the answer, work it out, and check whether your answer will be right. So, question number 3, you have to find the total perimeter of a sector. After quoting the formula, you substitute the values, and you get this answer. Then number 4, which is the last but one question. Here I said, from the diagram below, the length of the minor arc is AB. So I've given the length of the minor arc to be AB. So I want you to find the minor arc AB and then the minor sector OAB. Each of them is a formula work. Just quote it and then you'll be able to solve it. There you go. So when you do it very well, you should get the following as your answers. So take note of the answers and check whether you get it right. Then our last question for the day is this. Okay? And your answer to this question, no, let me get the question back again. Maybe you are trying to take a screenshot of that. So take a screenshot of this quickly, and then I'll give you the answer so that we end today's section. On our next meeting, we'll be looking at the part two of Mensuration 1. I'm sure you've enjoyed today's lesson and you've learned a lot. This has been the SHS2 on Joy Learning, Core Mathematics, and the topic has been Mensuration 1, Part 1. My name is Evans Odei. Thanks so much for watching. Bye.
Subscribe to our YouTube channel, Joy Learning TV.